Alright, what we're going to have a look at today is this, and what this is a small amplifier. And why I wanted to build this is because every now and then I run into a situation where I want to drive a very specific signal into something that I want to test or try out or whatever at a little bit higher power than my signal generator could put out. Most signal generators are, signal generators are not drive 20 watts of power into something generators. So most of them don't have the capability to produce all that much output current. And especially not the sine wave generator I built in the previous video, the one with the vacuum tube output stage. That one is actually below a milliamp in maximum output current. And even at that point, that half a milliamp or something, the sine wave is quite badly distorted. And same goes for my professional Philips signal generator. That one, it can supply a little bit more current, I think 10, 20 milliamps, something like that. But still, want something that can drive 100 or 200 milliamps. So this is why I built this. And it's actually relatively simple. And it's relatively simple because of the fact that most times when I want power, I don't really care about signal integrity, let's call it that, so much. So if it's a little bit distorted, so be it. I'm not trying to do very high precision and high power because that would be relatively difficult and I don't need that. So relatively simple design, Class B amplifier. Alright, let's look at what I came up with here. We've got our signal coming in here on the pin, and then we've just got a basic non-inverting amplifier. As an op-amp, I chose the LF411, but you could choose basically any op-amp you'd like. I've got the second resistor for the gain set. I've got on two pins that I brought out on the board here, while the other one is a surface mount package on the bottom. And what I want to do here is I want to make this adjustable on the front panel via a switch. One issue with that is, now obviously you've got your feedback signal running through the front panel, and that is not ideal design-wise. And if we're doing something that should be either high precision or high frequency or any of these, or very robust, we'd probably not do that. But since we're mostly going to stay, let's say, below 50 kilohertz, and I don't care that much about signal integrity, I think this should work fine. I've got a coupling cap. This has no value written on it because I experimented a little bit with that. At the moment I've got 330 nanofarads in there, which is with the input and output impedance and everything. That should work relatively well for the sort of frequencies we want. And then we've got the actual output amplifier, which is another LF411, two complementary transistors, and just a split supply that's also running through the op-amp. It's all running off the same supply. Keep it nice and easy. And the output we're just deriving from this point here. There's on the schematic there's no pad here, but the actual board has an output pin here. So power supply also kept very simple. We've got a transformer. I want to use this one. 20 volt split transformer, so 20 center pin 20, going through a bridge rectifier, capacitors, 7815. I know it says 7805, but I don't have the 7815 modeled up in a library, so because they're basically the same, I use the 7805. It has the same footprint, it has the same package, so this is a 7815. But you could obviously, if you wanted different output voltages, you could put any sort of, if you want 5 volt split, you could put 5 volts in there. And then you've got an amplifier that has a maximum output swing of, well, about 10 volts. A bit less than that. 2 more capacitors, 2 more capacitor values, 200 nanofarads and 2000 microfarads. And that's basically all. On the board layout, I initially wanted to mount all of this on one heatsink that would sort of go here, but then I later decided not to do that. So now we've got 2 small heatsinks here and a little bit of a larger one for that. And in the case this is going to be bolted down, it's just glued on at the moment with this heat transfer tape, which is not that great. But in the final design, so it doesn't fall off, it will have a little bracket going like this. If I would have known that I put separate heatsinks on here, I would have probably moved these somewhere around here. And, I don't know, somewhere around here, move the amplifiers towards the output stage a little bit. That would help with, that's the wrong side of the pointer, it's actually a brush, paintbrush. That would help with the signal integrity a little bit, because we wouldn't have to route raw power around here into the regulator, and we could keep them sort of separated, so that the power supply here and the amplifying section here. Although it works out relatively well like this, and I think this is due to there being a fair amount of filtering before a regulator. So the power coming back here to the regulator is already pretty clean in terms of ripples, so it doesn't interfere with circuitry a lot. And then also the amplifiers are sitting on their own little sort of island of clean power down here. Yeah, and I think that's all I have to say about this. So how about I hook this up to some test gear, and we'll have a little look at the output waveforms and stuff. Let's just have a look at this test setup here. We've got power coming in here to the transformer, coming out here into the power supply. We've got the input from the signal generator coming into the input here, down there, and the ground from the signal generator hooked up to ground. Then I've got 2 probes. The second channel of the oscilloscope is going to the input, and it's just going to show us what's on the input. And the other probe from the oscilloscope is connected to the output. And then I just have this small box of resistors here, also connected to the output, so we can apply a load. It's currently in the 220 ohm position, but I have 15 and 5 ohms here. So we can try that too. Okay, I think we're ready to go to the oscilloscope and have a look. Alright, here it is on the oscilloscope. The bottom trace is the input signal, and the top trace is the output signal. And I've got the top here set to 20 volts per division, and the bottom trace here I have set to 10 volts per division, and the preamplifiers at the moment it's set to ×2 amplification. And if we sort of overlay those traces, you can see that is perfect. And we're also perfectly matching the input waveform. And really, it looks quite good. We can zoom in here a little bit. Look at the output. That looks really quite nice. Alright, so that is obviously with almost no load on it. but if we go to a little bit of a higher load, we're at 20 volts per division here, and we're connecting this to the 15 volt tap at the resistor box. We can't do that for too long because resistors are going to get quite hot now very shortly. But we can see that it's still working quite well. The waveform is still looking relatively clean. And I mean, if we go to the 5 volt tap here, should actually slowly see something happening. So what happened there towards the end is I broke it. I accidentally shorted out the output, and that's why you see there's no signal in the end. And as you can tell from the board looking different now, I've repaired it, and it took me quite a while. So what happens is one of these transistors shorted out, which then took with it the other transistor. That in turn, as far as I can tell, blew the rectifier, and which then, blew both regulators. I didn't even know you could break. Well, I've hardly ever seen a 7805 or something like that fail. I mean, yeah, of course it does happen, but usually in stuff from the 80s, running at 70 degrees for 30 years, usually these are very reliable and very resistant to abuse. But apparently, yeah, with the rectifier being a straight short across, apparently they didn't like just 60 volts AC across them. So yeah, that all failed. Which of course then took out the op amps. So I had to replace every single semiconductor on this. Which was only slightly annoying. Which you can also see on doing that, I hit this potentiometer, which is the zero adjust for this op amp with the soldering iron. This is, luckily enough, was set in the right position, so this is just going to stay like that forever. It's a trim adjustment anyway, so if this were a product, you'd probably Loctite it down. I mean, yeah, it's not moving. And resistance value is still okay. I mean, it should work. This is damage outside of the actual resistive element. It's just on the, if you look at this, it's just on the side and then on this top part here, which normally turns. So yeah, that's okay. So what did I do to prevent this from happening again? I actually thought I had designed this in a way that it wouldn't fail if you shorted it. Because I'd thought these 7815s would current regulate to 1.5 amps, and transistors can handle way more than that, so we should be fine. And the rectifier is a 1.5 amp type, so that should be okay. Well, problem is there's relatively large filter capacitors behind the regulators. So when you short this out, I think what happens is they just dump all the stored energy into the transistors, which makes the transistors fail. And it's then this cascading failure going through it from there. So what I did is, first of all, uprated the bridge rectifier, which I think I'd actually had to do, but I did it anyway. And this is going to be mounted somewhere in the case now with the fuses. So I removed these 2 pins here, and the input is just where the old rectifier is at. And then, as a simple measure to prevent an overcurrent situation, where the output pin was located before, there's just this big 5.6 ohm resistor here. Position is not ideal because it's sitting right next to this capacitor and it's going to cook it, but as long as you don't draw an amp for it all day for 5 years, that should be fine. So it works now, and it is short circuit proof, which for something that you're going to use on a test bench is almost a prerequisite, because it just happened to me while testing. You're going to short out stuff when you're hooking up probes, so it's just going to happen. So it has to be fairly robust. Okay, so I think the last thing we should do is just feed in the same signal as before, and then just hook a meter up to this port and see how much current we get out into some sort of load. Right, so I've got the same test setup as before. Signal generator goes in here. Output is taken from here, goes through the resistor box, and then comes in back. Down here, the transformer actually, and this is the negative lead from the signal generator. The meter is set up for amps AC, and I'll just connect it to a 15 ohm load, which we get about 350 milliamps, which is quite substantial, and into 5 ohms we get about 700, and if we short it out we get about an amp, but without the thing blowing up now, which is nice. Okay, great. Obviously one problem with this resistor is now as we go up in current, while before you could see on the oscilloscope as I went down the resistor values for the load, we did get almost no drop in voltage. Well, now we're obviously getting quite significant voltage drop, which for this application doesn't matter too much though. We're feeding this from signal generator. We've got at the moment ×2 amplification, and if we don't have enough output voltage, I'd just crank up the signal generator. And most times I'm just going to use this as a buffer anyway, then the gain is adjustable, so on and so forth. I think it's a pretty good solution like this. If I had known this from the beginning, I'd probably design it a little different, put current regulation somewhere before here, so I don't have to do it on the output, but that's what it is. Now all that I have to do is put this in its case, which is sitting right below it, and I think then we'll finish up this project. Alright, here we have it. That is the amplifier in its case. The top switch is the amplification. I did go for 2, that's this setting, and 100 times amplification. You can see my printer had some trouble with bed adhesion here and here, but that's fine. The input comes in via this BNC jack here, because I'm usually going to feed it from a signal generator, and I can just have a BNC to BNC cable. Output to 2 banana plugs, power lid, fuse cable on the back. I think that's all I have to say about this. I'm pretty happy with this, with how this turned out, and I'm sure I'm going to use it in one or the other video in the future. So I hope you enjoyed this video, and I'll see you around.